Okay, guys. We're going to be starting Unit 3 today, and we're done biology. Unit exam is this Wednesday. Make sure you're going over all of the review material that I posted last week. Okay, do the review package, practice test, all that kind of good stuff. And what's the most important thing you can remember to do on that test? 3 words. Level of detail. Okay, you must have detail in your answers. Okay, tell me what you know. Don't keep anything to yourself. Okay, because the worst thing is when we're going over the test, we look at that. Well, I knew that. I sure wish I'd written it down. Yeah, don't be that person. Okay, be the person who's looking at that and go, I knew that, and I wrote it down. I am so smart. SMRT. I mean, SMART. Yeah, okay, that's you guys, all right? We want to make sure that we are writing everything down, okay, so that we have it all and we get all the marks possible. So, for the third unit is physics, okay? And in this unit, we are going to be going over a lot of stuff to do with energy, work energy theorem, okay? So, probably close to half the unit is about energy in some way, law of conservation of energy. Okay, that kind of stuff. And the other part of it is that we have to learn the basic tools that are necessary for you to have in Physics 20. Okay, and that would be things like manipulation of formulas, algebra, understanding what, speed and velocity, distance, displacement, acceleration, okay, all those things, how they relate to each other, graphing. Okay, we'll be doing quite a bit of graphing in this unit. Graphing is an important tool for all of the sciences, but physics especially. So we'll be looking at a few different kinds of graphs, but there's a fair amount of, math in this unit. That said, you will need a calculator for this unit. Okay, so make sure you bring your calculator to class kind of going forward, because you're going to need it. We're doing a lot of calculations. Okay. All right, so for today, we are going to look at the different types of energy, how energy is converted, transferred, okay, just kind of the basics, a little bit of history on energy, and stuff like that. Kind of the way we start every unit, a little bit of the history of that particular topic. Okay? So, first thing we're going to look at is this really blurry picture, okay, of some people doing the Inuit blanket toss. Okay? The Inuit blanket toss was actually, it's more ceremonial now than anything else, but it served a very useful purpose hundreds of years ago, in that the place where the Inuit typically live is very flat. It's a polar grassland, basically. The tundra is what I'm talking about. So you can only see so far, and then you've got the horizon. And there's no mountains or trees or things like that that you can, climb to see further, okay, like you could here. If you just go on top of a ridge or you climb a tree and you can see farther. Well, in the tundra, you can see in the background here, like, it looks like Saskatchewan. Okay, it's just flat. And so you couldn't really sneak up on like a herd of caribou. Okay, or something like that if you were hunting them, because they'd see you coming and they would just take off. So what they would do is they would put the smallest person in the tribe on the blanket and they would throw them up in the air as high as they could. Okay, that person then gets that added elevation. Okay, it allows them to see over the horizon, okay, see where the herd is, and then they can kind of encircle them, okay, from all sides and hunt them more effectively. Okay, so that was kind of the purpose of the original Inuit blanket toss. Okay. In order for the Inuit blanket toss to work, we have to take energy and convert it from one form to another several times. Okay? Where does the energy to throw the person up in the air come from? Looking in that picture, all the people are holding the blanket. Where does the energy to throw the person come from? Oh, I can wait. Nico.
The people holding the blanket.
Okay, the people holding the blanket, where did they get the energy from? From the food they would have eaten. Okay, so where would the food that they would have eaten got its energy from? Now it's getting trickier.
Any plants that those animals would have eaten?
Right, and those plants would have got their energy from
The sun.
the sun. Okay, are there a lot of energy conversions going on here? I mean, that's like taking it to the nth degree. It's a little bit ridiculous, but that's where the energy originally comes from. Okay, and by the same token, if anyone ever gives you a hard time about using a gasoline-powered vehicle, you can tell them it's okay that it runs on solar power, because it does. The fossil fuels that you are using to power your car were once plants who used the sun for energy. So it all works out in the end because originally that was energy from the sun. I'm not saying you'd actually do that or that there's not a real threat to the climate change and all of that. I'm not saying that, but hey, it's something you can do if someone ever gets uppity with you. All right, so in this Inuit blanket toss, what we're looking at is, yes, people are pulling hard on the blanket. Okay, they're exerting a force. When they do that, they do work. Okay, work is a change in mechanical energy because the work that they do is going to change the mechanical energy of the person on the blanket. They're going to go from stationary to in motion and moving vertically. All right, so two kinds of energy about that person are going to change. Their potential energy, because they're going to go higher, and their kinetic energy, because they're going to go faster. Okay? Those two things are what make up mechanical energy. So any work that we do will change the mechanical energy of whatever we do the work on. Okay? If I'm pulling a desk along, okay, I'm going to change its kinetic energy. I'm going to change its speed. Does everyone kind of follow that idea? So there's a lot of energy conversions that go on here. There's the work that changes this person's mechanical energy. Their kinetic energy increases, and then they go up, and their potential energy increases, but their kinetic energy decreases. When they're at their highest point, they have no kinetic energy, all potential energy, and then they start falling back down, and their potential turns back into kinetic, and if the people holding the blanket aren't ready, they'll be hurt. So the people holding the blanket have to be ready to do more work. Okay? That is to take the energy away from that person and catch them safely in the blanket. All right? So there's a lot of little conversions of energy that go on in something that's otherwise pretty simple. You put somebody on a blanket and throw them up in the air. Okay? But there's lots of little things to do with energy that go on. Okay, so definition of energy is the ability to do work. I would add that to my notes package because it's kind of important. Okay, so the big thing with energy, the thing that makes, or that at least made energy difficult to describe or quantify, okay, or anything like that, okay, was that energy is not matter. Okay, it's different than matter. Okay, it's, well, energy doesn't have mass. It's not made of anything. Okay? So it was difficult for scientists to do experiments, okay, where they can measure it. Because it's not something you can like keep in a jar. Okay? Does that sort of make sense? You either have it or you don't. It's your ability to do something else. Okay? So energy is the ability to do work. I either have it or I don't. But I can't like pull it out of me and go, here's my energy. See it? Because you can't. Energy is not something you can always see. If it's light energy, you can see it. If it's sound energy, you can hear it. But you can't catch it. Okay? You can't hold it in your hand. It's not like that. And so it was very difficult for people to explain exactly what energy was or do any experiments that could really capture it. Okay? So scientists were convinced early on, okay, that there was this thing called energy, but it was difficult to describe because it was an abstract idea and not a material object. Okay? Experimental evidence supported the theory that heat was a form of energy. It's actually not. Heat's a transfer of thermal energy. Thermal energy is what we would typically call heat. Okay? And that it can be converted into other forms following certain principles. Okay? So yeah, we can always convert energy into different forms. Okay? If I drag this desk along the floor, okay, where did the energy for the desk to move come from? From me. The desk moved and it made noise. It's two forms of energy. It converted the chemical energy that was stored in my cells into mechanical energy by pulling the desk, and the desk moved, gained kinetic energy, and made noise, which is also a form of energy. Okay? So it's easy to convert energy from one form to another. It happens all the time. You're doing it right now. Okay? You might notice that over the last few days now that the weather's turned cold. When you come in here in the morning, it's cold in here. It's because I use you guys to heat the room. Okay? If I turn that thing on, even the slightest little bit, it has like a gradient on it that would imply you can turn it on a quarter of the way or halfway, but you can't. It's on. As soon as it's off of off, it's on all the way, and it just turns into a sauna in here. Okay? So I instead use the fact that as your body uses your food energy, you generate heat. You're 37 degrees Celsius. The air temperature is around 20. So you're gradually going to heat the room. And I save the taxpayer money. See, everybody wins. Except you, who have to be cold for the first period or so. Okay? But we're just converting one form of energy, chemical energy in our food, into heat energy. Okay? It flows outwards. All right, so what we're going to do is we're going to look at the different forms of energy that are present and kind of how they work. All right, so chemical energy is the one we're going to do first because, well, it's the one that basically society runs on. Okay? Like it or not. The bulk of our electrical energy, heat energy, okay, all of that stuff comes from converting chemical energy in some form into something else. Okay, so the early alchemists, so this goes way back, okay, they knew that there were what they called hidden secrets in chemical reactions. Okay, that is that some chemical reactions did cool stuff, okay, or released different forms of energy. And what they found was not all things release the same amount of energy. Okay? It was actually Lavoisier, okay, who did an experiment to kind of quantify this. He took different kinds of fuel and he burned equal masses of them. So he burned like a kilogram of wood, a kilogram of fuel oil, a kilogram of coal. Okay? And he found that when he burned these different fuels, they made different amounts of energy. That is, they made more heat or thermal energy when they were burned. Okay? So that would imply that they had something stored, a hidden secret, inside. Okay? But some of them had more hidden secrets than others because they could change the energy more. Okay? So that form of energy is what we call chemical energy because it's releasing the potential energy stored in the chemical bonds of that material. So let's say you're having a barbecue and you're using your barbecue. Okay, so your barbecue probably runs on propane. So this is what a molecule of propane looks like. C3H8. Okay. When you combust or cause a combustion reaction between propane and oxygen, what happens is every one of these bonds, okay, gets broken. Every time you break one of these bonds, energy is released in the form of heat or thermal energy. Okay, so propane has a lot of bonds in it. So when you burn it, it can release a fair amount of energy. Okay, which would have more energy? Propane or octane?
Octane.
Octane has more energy. Why? It has more bonds. It's a bigger molecule. Okay? Where do you hear octane associated with? You guys ever fill up your car? Gas? Okay? There's different grades of gas, right? There's regular, there's mid-grade, and there's premium. And the difference between them is the amount of octane in each one. Okay? Regular gasoline is 87 octane. Okay? Mid-grade is usually 89, and premium is usually 91. Okay? So there's more octane in premium, thus it burns hotter. Okay? Don't put premium in your car if it's not supposed to have it. It burns too hot and you'll foul your sensors and the check engine light will come on. And then you have to take it in and have someone check it out, make sure you haven't wrecked something in your car. So if your car doesn't say put premium fuel, don't put premium fuel in. It is not going to make your car run better, okay, long term. Okay? It might, like for that one tank, it'll probably be okay, right? Okay, so chemical energy is the energy in the bonds of any molecule. Okay, if we're having a campfire, okay, the cellulose molecules that make up wood, okay, they get broken, they get turned into woods. Okay, so chemical energy is the potential energy stored in the chemical bonds of compounds. Okay, and as I said, society basically runs on this. Okay, especially North American society. The bulk of our electricity is produced by burning coal. Okay, burning coal or other fossil fuels. Obviously, most of our vehicles, okay, still the vast majority of our vehicles are internal combustion engines, which require chemical energy. Okay, yes, there's getting to be more and more hybrids and electric vehicles. Okay, but in the end, if you buy an electric vehicle in Alberta, are you helping the environment as much as you maybe think you are? Where does the energy come from to charge your car? From burning coal. Okay, so you can kind of distance yourself a little bit. Like lots of people say, I bought an electric car because I want to do my part for the environment. And even in Alberta, electrical cars are far more efficient than combustion engines. But still, as soon as you plug it in, the coal-fired electrical plant that is sending electricity to your house has to run harder and burn more coal in order to charge your electric car. Okay, so you are slightly reducing your carbon footprint, but not as much as if you had a bank of solar panels in your backyard that was attached to the charging station that charged your car. Then you'd really be helping out the environment. Okay, but know that we don't maybe do as much as we think we do. It's one of those things that we have to think about a little bit more when we're making our decision. Right? I'm not saying don't buy an electric car. Totally buy an electric car. They are better on the environment than gas-powered vehicles. I'm just saying you have to know where your electricity comes from. Okay? Does that sort of make sense? Okay. All right, then we'll talk about electrical energy. Okay? So electrical energy is the work done by moving charges. So when you charge up your phone, okay, you plug it into the wall, electrons go through the cord and they go into the battery. Okay, so the current goes into the battery, okay, from the wall, and the energy of those moving charges is used to increase the potential difference of the lithium-ion battery. Okay? When you unplug it, that current goes the other way. Now, the energy of moving charges is actually coming from the lithium-ion battery. So as those charges go out of the battery and into the phone, they slow down. When they slow down, they give off some of their energy. Okay? And that's the energy that's used to power your phone. As your battery is used up, okay, the speed of those charges gets slower and slower and slower, and so it provides less and less energy. It gets to a point where it can no longer safely power the phone. We call that, now it's dead. Is it really dead? There's actually still a fair amount of energy in your phone's battery when we consider it to be dead. It's just not enough to power the phone anymore. Okay? If you were to truly, completely discharge a battery, the charges would not move at all. There'd be no difference between the positive and negative side of the battery. Okay? The more charged it is, the greater the difference between the positive and negative sides. Okay? And so the electrons flow more quickly, the more charged your battery is. Does that sort of make sense to everybody? Okay? So that's generally how a battery works. Rechargeable batteries you can push back, okay? But regular batteries you can't. Okay? You can't put them back to their original state. Incidentally, how do you check if a battery is live or dead, like a AA battery.
Don't you like, you drop it down or something from like not very high and then like if it stays up, I don't know, like.
No, you're right. Yeah, okay, you do the drop test, okay? So if you drop the battery and it stands up, it's still good. I might have that backwards. Okay, so anyway, in battery, you got the positive end, you got the negative end, right? So you got the negative end, you got the positive end, and what happens in a normal discharge cycle is the electrons, the charges go from one end to the other. Okay? Well, as a battery discharges, more of that mass ends up down at the bottom of the battery. Okay? So if it's discharged, it will stand, it'll tip over because positive's at the top. Okay, so if I drop it like this, and it's like just from about this high, you don't have to drop it from way up here, it'll definitely fall over. Okay, drop it from about 2 inches or so. Drop it, if it stands up, that means all the mass is at the bottom. Okay, drop it and it falls over, it means more of the mass is at the top. Okay, if more of the mass is at the positive side, that means the battery's dead. That means it tip over. Pretty sure that's the way it goes. I could have it backwards because I don't remember which way is which. Does that make sense? Okay, so it's moving charges, and as long as those charges can move, electricity can be generated. Okay? Or electrical energy can be generated. All right, so that thing right there, that is the great-great-great-granddaddy of the AAA battery. That is the Volta pile, made by an Italian scientist named Alessandro Volta. Okay? And what he had was metal discs that were separated by moistened paper. And what would happen was he could actually get an electrical current generated from that because the metals had the ability to have kind of a chemical reaction because of that moistened paper with each other that would allow electrons to flow from one metal disc to the other. And eventually, if you connected the top one to the bottom one, it would be a wire. You put something attached to that wire and it would power it, like a little light bulb or something like that. Okay? And that's the same technology we essentially use now in our batteries. Okay, questions on electrical energy? Okay, the big thing is, it's the work done by moving charges. Okay? All right, now, magnetism. Magnetism also goes along with electricity because magnetism can have electrical effects and electricity can have magnetic effects. Okay? This was discovered by 2 different people, Faraday and Oersted. Could this be something that might end up on a quiz or a multiple choice item? These people's names?
Yeah.
Yeah, possibly. Okay, so what Oersted discovered, quite by accident actually, was that there is a magnetic area of influence around a wire that is carrying a current. So as the electrons, the charged particles, are flowing through this wire, they actually create a magnetic disturbance. It's actually why, in addition to safety, most wires are insulated. That is, they have like a rubber or plastic coating along them, okay, that kind of shields them. So what he was doing is he had a compass because he was doing an experiment with magnets, and he had an electromagnet, and he plugged in the wire, and it just so happened that the compass was sitting under the wire, nowhere near the magnet. Okay? And instead of pointing north, as soon as he plugged it in, the compass aligned with the wire in exactly the same direction the electrons were flowing. Okay? So if this direction was north, the compass flipped and turned this way, following the flow of electrons from negative to positive. All right? Which indicates, I mean, the only thing that can make a compass change direction is a magnetic field. So there had to be a magnetic field directed that way in the wire because of the current. As soon as he unplugged it, compass pointed north again. Okay? Because then the dominant magnetic field would have been the Earth's magnetic field. As soon as he turned the wire back on, it would follow the wire again. Okay? This can happen, not that you guys would know this because you probably never had one of the old style tube televisions. Right? You guys have probably only ever had flat screen TVs, but back in the day we had these things called cathode ray tubes, okay? Big glass tubes that you would watch TV on. They were square, okay? They weren't like this one. Okay? And you could mess up the picture with a powerful magnet. So if you had like a speaker or something like that was plugged in and you put it near the TV, you could stretch people's faces on the TV. Okay? Because the magnetic field from the magnet would pull the charged particles that were making the screen's picture over in a different direction. Okay? So you could, like, their face would literally just go over because the particles that were going to make that picture got pulled out of alignment and they ended up somewhere else on the screen. Okay? It wasn't actually very good for your TV, but you could do it if you didn't care. Okay? And it would mess it up. All right? So, electricity can have magnetic effects and vice versa. Okay? Michael Faraday discovered that if he coiled up a wire and pushed a bar magnet through it, that it would move the electrons and generate an electrical current. Okay? So he basically just hooked up a voltmeter to this coil, and then as he pushed the magnet through the coil of wire, the electrons ran away or were repelled by the magnet and pushed through the voltmeter, creating a current. So he actually kind of came up with the idea for the first alternating current generator. If that magnet keeps going in and out of the coil, it keeps moving the electrons in alternating directions, creating an alternating current. Okay? So kind of the idea behind the generator. All right, so that's Oersted and Faraday. Okay, so Oersted discovered an electric current in a wire could produce magnetic effects. I underlined that. Might be a good idea for you to underline that. Okay, and then obviously Michael Faraday, this guy, okay, moved a magnet through a coil of wire and observed that that caused an electric current to flow through the wire. Okay, and the next thing is that this could also be used to make electricity through something called a thermocouple. Okay? So a guy named Seebeck, okay, discovered that if you put two different types of metal, so he had an iron bar and then he had a copper kind of U-shaped piece of metal that sat on top of it and they were kind of soldered together. Okay? He discovered that because these heat up at different rates, that you could get an electric current generated by heating up two different metals. Okay? So what happens to the particles in something when you heat them up? Something gets hotter, what happens to the particles inside it? Sometimes it'll expand a little bit, but why does the whole thing expand? What are the particles doing that cause it to expand?
Particles move a lot faster.
They move faster. Okay? So, since iron and copper heat up at different rates, if you start heating up the iron, the particles start moving and they start running into each other. Okay? And when they run into each other, they transfer kinetic energy and the particles can kind of transfer this energy through. Well, copper heats up way faster than iron does. Okay? And so as you start heating up the iron, that energy gets to the copper and the heat travels through the copper faster than it does through the iron, and it creates a difference in the rate at which electrons move, which is a current. Okay? And what he discovered is if he set this up and put a compass needle in the middle, as soon as he started heating this up, the compass needle would align with the bars. Only reason for that would be a magnetic field around a current-carrying piece of metal. Okay? Does that sort of make sense? We actually use this in hybrid cars. Okay? Anybody in here have a hybrid car? Okay. So in a hybrid car, in the brakes, specifically in the rotors, that's the shiny part you can see through the wheel, okay, that the discs clamp onto. In that rotor are thermocouples. And when you apply the brakes get really hot. But because they have thermocouples in them, that heat gets turned back into electricity, which charges the battery. Okay? We recently bought a plug-in hybrid, okay, for our family, and now it's like a challenge for me because when I'm braking, it actually has this little gauge that comes up that tells me how much of my kinetic energy is recaptured and turned back into electricity. There's a little gauge, and sometimes I can get it to be 100%. So it's become a game. Okay? If I slam on the brakes really hard, I get like a terrible percentage, but if I brake really slowly and let it kind of slow down gradually, okay, I get 100% return. Right? So it's actually a pretty smart thing to do if you're trying to maximize the efficiency of something. Okay? in most cars that don't have thermocouples in their brakes, that energy is just wasted. It turns into heat, it dissipates into the environment, and it's gone. Okay? But in a hybrid car with thermocouples in the brakes, it's used to replenish the battery. So it's not all wasted. Okay? Some of it can go back, okay, and be useful electrical energy. Okay? We can also use this in a circuit breaker. Okay? How many people have ever popped a circuit breaker at home? Plug too many things into one outlet, and then everything goes off in the room, and you got to go downstairs and flick the breaker, the switch. Okay? Breakers work very similar to that. They measure the amount of heat in the circuit. Okay? If it gets too hot, enough of a current is built up that the breaker will pop. Okay? And that'll open the circuit, no more electricity can flow through it, and it can cool off. Okay? This has happened to me a bunch of times with our garage door opener, which we have to replace. Okay? If it's too cold outside, the garage door opener has to work really hard, and the circuit will get hot, and the breaker will trip. And if I go down there and just flick it because I'm upset and I want to get the door down, okay, it'll just pop back off again because the circuit's still too hot, and there's still enough current going through that thermocouple to keep popping the breaker. So I have to wait. Okay, wait for the circuit to cool down, and then flip the breaker back over, and it'll hold. Okay, but it's a very important safety feature in your home that prevents electrical fires. Okay, before circuit breakers, there were fuses, which you'd have to like pull the fuse out and put a new one in. Okay, and they would just burn out if they got too hot. That little wire inside the fuse would just ignite, opening the circuit. No more electricity could flow through. Okay. All right. Nuclear and solar energy. Okay, so nuclear energy is the potential energy stored in the nucleus of an atom. Any change to the nucleus of an atom will release energy. And there's two ways to change the nucleus of an atom. What are the two kinds of nuclear energy? Read.
Fission and I forgot the other one.
Fission and, let me put them together,
Fusion.
fusion. Okay? Fission and fusion both alter the structure or the nucleus of the atom. Fission means you shoot something at it and the atom splits. That's what most of our nuclear energy is. Okay? Is fission. It's easy to control. Okay? The fuel is easier to produce. Okay? That kind of stuff. So we typically, if we have nuclear power, we use fission. That's and especially in Europe, they use tons of nuclear fission for electricity. I don't know if you've been monitoring what's been going on in the Ukraine, but they've had to turn their reactors on and off multiple times, okay, because of all the shelling that's been going on. Because obviously that's not something you want to have a problem with. And unfortunately, the Ukrainians are quite familiar with that because what nuclear power plant was in the Ukraine? Think back to the 80s, they made like a mini-series about it. Starts with a C.
The Chernobyl reactor.
Yeah, Chernobyl. Okay, Chernobyl is in the Ukraine. Okay, so they're very familiar with the dangers of nuclear energy. Okay, so they're being abundantly cautious. Okay, those plants all use the same technology. Okay, and that is that they are shooting neutrons and particles at pieces of uranium, causing the uranium atoms to split and release huge amounts of heat. Okay, that heat then evaporates water into steam, and the steam can turn a turbine, which generates electricity. Okay, essentially all electricity is generated the same way. It's how they get their heat. So in a coal-fired plant, we use coal to evaporate water, turn it into steam, and then the steam turns a turbine. In a nuclear power plant, we use nuclear energy to evaporate water, turn it into steam, and turn a turbine. Okay, generally that's how all of our electricity is generated, some sort of turbine system, even a hydroelectric dam. Okay? Hydroelectric dam, the water falls over the dam, hits the turbine, turns the turbine, makes electricity. Okay, so even tidal power, wind power, okay, if you've ever been down like by Pincher Creek, okay, they've got all the big wind turbines, same thing. Okay, the wind turns the turbine generates electricity. Okay. All right, with fusion, fusion is different. Fusion is the atoms being forced together to become one larger atom. So rather than taking one large atom and splitting it apart, you're now taking really small atoms and forcing them together. And this is the energy that powers the sun. Okay? To give you an idea, anything that has mass can exert gravitational force. Okay? So the Earth has a gravitational field. That gravitational field is so strong that it holds the moon in orbit around the Earth. Okay? And it holds us against the surface of the Earth. Okay? But you and I also have gravitational fields. They're just so incredibly puny that they don't do anything. Okay? We're next to the Earth, whose gravitational field is enormous by comparison. But compare the Sun to the Earth, and you've got an even larger gravitational field. The Sun's gravitational field extends all the way up past Pluto into the Oort cloud, okay? Which is so far away it's almost like boggles the mind to think. Okay? Really, really far. That gravitational field is really big because this is the mass of the Earth. This is the mass of the Sun. It's millions of times bigger. Okay? And as a result, has way more gravity. So much so that when you're on or in the Sun, if you're a hydrogen atom that's part of the Sun, you weigh so much because of the Earth, or the Sun's incredible gravity, that you are fused together, squished literally together with another hydrogen atom to form helium. Okay? The gravity is so strong that it literally crushes atoms together. Okay? When that happens, vast amounts of energy are released. Okay? Because the Sun is so big, there's a lot of hydrogen there to fuse. Okay? Which is why it's been, perking along for about 5 billion years or so. Okay? It's got a lot of energy it can go through. And eventually it's going to run out. Not tomorrow or the next day. Okay? It's not something we have to worry about. Okay? But in another 3.5 to 4 billion years, eventually it'll run out of hydrogen because it'll have fused it all into helium. But that's okay. The Sun is big enough that it can start fusing that helium into other things. Okay? But eventually, the stuff it's making from that fusion will get too big, and the Sun's mass is not sufficient to keep fusing it, and the Sun will just kind of burn out. Okay? It'll swell, and it'll become a red giant, which will envelop the Earth, and then it'll just kind of go, I don't have it in me anymore. And it'll just shrink down to a little white dwarf, and that'll be it. Okay? Again, it's not going to happen tomorrow. Okay? It's billions of years away. It's really not our problem. Okay? But it will eventually happen. Okay, so solar energy, anything that we use, okay, captured by solar panels or even like thermal capture. Okay? In Drake Landing, they use thermal capture. Okay? All the solar stuff that's on the Drake Landing garages there, that's actually water going through those panels. It's a thermal capture thing. The hot water heats up, and they actually use it to heat things. Okay? And then they also have some photovoltaic cells on each house that actually convert it directly to electricity. So there's different kinds, but solar energy always comes from the hydrogen nuclear fission that is going on, fusion, in the Sun. Okay. Now, motion and energy. So this stuff is all about kinetic, gravitational, and mechanical energy and work. This is the stuff we'll focus the most on in this unit. Okay? So Gottfried Leibniz, who was a German philosopher, okay, he kind of came up with an explanation for this. This thing is Newton's cradle. It got Newton in a lot of trouble. Okay? Because you got to remember the time when Newton lived. People were much more likely to believe in things like witchcraft and stuff like that. Okay, so when Newton kind of devised this thing and then said, "Hey, everybody, look at this," and pulled the little ball away and let it go, okay, it hits this one, and then what happens to the ball on the other end? Flies off, right? You or I look at that and go, okay, because we understand kind of how it works. But when Newton first did that and showed that to people, they're like, "You're a witch." And he's like, "No, I'm not. You can do it." "Hell no, I'm not touching that. I'm not a witch." Okay? "You're a witch. I'm not going to touch that." Okay? And so it got him in a lot of trouble because people were like, "Well, you must be a witch or that wouldn't happen." Okay? Kind of thing. So in reality, all that happened was Newton did mechanical work. He lifted this ball away and then gave it gravitational potential energy. So when they let it go, gravity pulled it back down and turned that potential into kinetic. The kinetic energy was transferred through the other spheres here, okay? And that made the one on the end fly off because there was nothing to stop it. The energy just transferred through the apparatus to the other side. Okay? Eventually it stops because every time one ball hits another ball, it makes noise. Okay? And that sound energy just dissipates out into the environment. Okay? Represents a loss of energy from the system, so eventually it slows down and stops moving. Okay? So, the idea here is that within mechanical energy, an object can have kinetic energy or potential energy or both. Okay? So, if something is above the ground and could fall, it has gravitational potential energy. If it's in motion, it has kinetic energy. And obviously, something flying through the air would have both because it's above the ground and in motion. Okay? The sum of an object's kinetic and potential energy is its mechanical energy. Okay? So all that underlined stuff, super important. We're going to talk about that stuff a lot in this unit. Okay, if you have mechanical energy, can you do work? Absolutely. That desk right there, right now, in front of Kate, does it have any mechanical energy? Can it fall? It's already on the floor, right? I mean, technically it could tip over, but it's not going to do that without help. So right now, it has no energy. It has no mechanical energy. It's not moving, and it can't fall. Okay? Now, if I pick it up, does it have mechanical energy now? What kind? It has potential. I'm trying to hold it still. Okay? I mean, it's moving a little bit, but yeah, if I drop it, okay, it could do work. Can potential energy do work? When I'm just holding that desk, could it do anything other than fall? I couldn't use that desk to do anything unless I drop it. Okay? Potential energy is exactly that. It is the potential to do work. Okay? It represents ability, but not until it's converted. It's actually kinetic energy that does real work. The object, once it's moving, yeah. Okay? Think about this. You're standing in the street for some reason, and there's a parked bus and a moving bus. Which one represents more ability to hurt you? The moving bus. Okay? The parked bus has no ability to do work. Therefore, it's perfectly safe to stand in front of it until someone gets in. Okay? But then it's got to be moving. Okay? The moving bus is not safe to be in front of. It has kinetic energy. It has mechanical energy. It can do work. It will change your shape in an undesirable way. Okay? But the parked bus doesn't. Now, what if you had a parked bus and a bus that was hanging from a crane? The bus hanging from a crane does have the potential to do work. Okay? I wouldn't stand under it, okay? But that's exactly why I wouldn't stand under it. It's got the potential to do work. If it were to be dropped, it would turn that potential energy into kinetic energy, and then, yeah, it could change my shape in an undesirable way. Okay? Is everyone kind of following that mechanical energy, potential, kinetic thing? Okay? If it's in motion, it's got kinetic energy. All right. So that means then if we go back to chemical energy is potential. It's not released until the object is combusted, okay, until it's turned into actual heat. Okay? Electrical energy is kinetic energy if the electrons are flowing. Electrical energy can be potential energy if it's stored in the battery, usually as chemical energy. Okay? So there's different kinds, right? All right, now, heat and energy. Okay? This is where people get kind of terminology mixed up, and I do it myself from time to time. Heat is not a form of energy. Heat is a transfer of thermal energy. Thermal energy is what we would typically call heat. Okay. All right, so the first ideas about heat, which is this transfer of thermal energy, okay, that were kind of put on paper, were by this guy here, Joseph Black. Okay? He observed that when you put a cold object in a cup of hot water, the cold object gets hotter. Crazy, right? But so true, right? Now, what he realized here was that energy, thermal energy, was flowing from the hot object to the cold object. Okay? He also, at this point, realized that you can't transfer coldness. Okay? And the way he confirmed that was whenever he did these experiments, okay, he could take something that had lots of energy, okay, and put something in that had very little, and the thing that had very little would gain until they were at the same temperature. But if he put a lot of something that was really cold into something that was smaller that was hot, they would still only get to a balance. If you could transfer coldness, you should be able to make things get colder. You can only transfer heat, okay? You can only transfer what you have. Coldness is a lack of thermal energy. You can't transfer a lack of something, okay? But you can transfer thermal energy. Okay? So the hot object is always transferring its thermal energy to the colder object. A transfer of thermal energy is heat. Now, back then, trying to explain that was difficult because, again, energy is this abstract idea. It's not matter. Okay? And so what they always ended up defaulting to was that there was some sort of fluid that would flow from the hot object to the cold object. The problem is this fluid had to be basically magical because it didn't have any mass. Okay? This idea of a fluid transferring energy from one thing to another would mean that matter has to be flowing from one thing to another, which would mean the hotter object should get lighter and the cold object should get heavier. Okay? But that's not what happens. Therefore, energy is not matter. Okay? It can just flow. So they had this idea of this caloric fluid that could just flow, which really wasn't a bad analogy for what was going on. Energy does flow like a fluid, okay, from one thing to another. All right, so his observations, okay, became the principles of thermodynamics, specifically the second law of thermodynamics, that energy always flows from hot to cold. Okay, and then this little bit down here, the transfer of thermal energy is heat. Okay, the transfer of thermal energy is heat. Okay, now heat and mechanical energy. So it's very easy to produce heat from other kinds of energy, but making heat do things that are useful is very inefficient. Okay? Unfortunately, it's also how we do basically everything, but okay, it's not the most efficient way to do everything. So in 1800, Benjamin Thompson, who for some reason changed his name to Count Rumford, don't ask me why, okay, he moved to Bavaria and became the Minister of War. Now, the job apparently of the Minister of War is to supervise the construction of cannons. So what he discovered was that, or what he observed really, was his workers were boring out these lumps of metal. Okay, that's how you make a cannon. Basically, you have a big drill and you bore out a big lump of metal to make a cannon. Okay? And then to make the cannon work, you just pack gunpowder inside this tube that you've essentially made. Okay? Put a ball in front of it and then light it, and when the gunpowder explodes, it shoots the cannonball out. Right? So to make cannons basically involved taking big hunks of iron and boring it out with a big drill. Well, when he was watching his workers, okay, he found that they would put a tea kettle on top of the cannon they were boring out. And then they would start turning the drill. Okay? And they would work really, really hard. Because it was hard work to bore out these lumps of metal. Okay? And as they were boring it out, eventually the tea kettle would boil. The lump of metal would get so hot that it could boil a kettle of water. And then they'd take a break. So it's kind of the invention of the coffee break. Okay? Because they would work really, really hard and generate so much heat that they could boil water on top of the cannon they were working on. Okay? Where did the heat come from for that? It came from the mechanical energy of the workers. Okay? They were turning this drill, which creates a lot of friction, right? Because you're basically just drilling out this thing. So it makes all that mechanical energy, all that kinetic energy that they were producing by turning the drill, okay, was turning mechanical energy into heat, or into thermal energy, okay, and that was being transferred to the water, and it would eventually boil. So he suggested then that thermal energy could be manufactured from mechanical energy, which of course we know is true. Okay? It's the same thing with your brakes. We just talked about that a little while ago. When you clamp the brakes together, the discs and the rotors get hot. Okay? You're turning mechanical energy into heat. Okay? When you rub your hands together and they get warm, you're converting mechanical energy into heat, okay, or into thermal energy, okay, by doing that. Right? So mechanical energy is very easy to convert into thermal energy, but it's difficult to go the other way. Okay. All right. Then, a little while later, Thomas Young, okay, linked mechanical energy to this idea of kinetic and potential. Okay? So he said, okay, so there's the mechanical energy that's being converted into thermal energy, but mechanical energy comes in two kinds, kinetic and potential, because if you drop something, it turns into kinetic. That kinetic can then be converted to thermal, and so on and so on. So it was kind of like a chicken and the egg kind of thing, okay, where they kept going back. All right? So that led to our current definition of energy, which is the capacity to do work. Any type of energy can obviously do work. All right, just about done with me talking. All right, now, Sadi Carnot, who was a French engineer, he found that you could transform heat into mechanical energy, but you could only do that when thermal energy flowed from hot to cold. So you had to have one thing that was really, 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 really hot, and another thing that was really, 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 really cold. And when the energy would transfer, if you put something in between, you could capture that flow of thermal energy and turn it into mechanical energy. It's actually how a jet engine works. Okay? In a jet engine, you have the part of the engine where the kerosene or the JP5 jet fuel is actually burnt, okay, or combusted. And then you've got the high altitude air, or even just normal air, okay, behind the engine that's much cooler by comparison. So naturally, the energy tries to flow from where there's a lot of it to where there's less of it. Okay? And if the plane is moving, there's cold air going into the motor and being pushed out the back by this flow of thermal energy from the front of the engine where it's hot to the back of the engine where it's cold. Okay? And if you put a bunch of fan blades in the way, as that air and energy try to flow through the engine, it turns the blades, which produces thrust. Okay? So a jet engine is really using this transfer of thermal energy to create mechanical energy. But you have to have a huge difference, okay, in temperature between one part and the other for it to work well. Right? If you were trying to use a jet engine in a place where there was very little difference in temperature, it wouldn't work very well. All right. Okay, and then the last guy we got to talk about is Joule. Okay? And oddly enough, Joule's like the most important person in terms of energy because, well, the units for energy are named after him. Okay? So what Joule did is he actually proved all of these ideas about mechanical energy and potential energy and their relationship to thermal energy by performing two fairly simple experiments. Okay? The first experiment was the falling block experiment. So what he did is he had a stationary block, pardon me, that had a thermometer in it, and he had a falling block. And they were just kind of, this was on a, like a set of cables, or, and he could lift up the falling block to a height. Now, once he lifts it up to here, what does it have? It has potential energy. Okay, so he proved that potential energy was exactly that, the potential to do work. Okay, and he did that by simply letting it go and having it smash into the stationary block. What do you suppose happens at the temperature on the thermometer when the two blocks collide?
It rose.
It rose. Okay? You can do a very similar experiment at home. Take a hammer and a piece of wood, not a table or something nice, okay? Like just a piece of scrap wood in the garage, okay? And just bang on that piece of wood 5 or 6 times, and then put your thumb where you were hitting it. It'll be noticeably warmer. Okay? All you're doing is, because you're stopping, or the wood is stopping the hammer, okay, that mechanical energy has to be converted into something, sound and thermal energy. That's why the board will get hotter. Okay? That sort of makes sense? So that's what Joule proved. He proved in this experiment that potential energy is a thing. Okay? Because the only place the energy to change the temperature could have come from was from the falling block. Okay? Which then, of course, led to him saying, the only reason the block had energy is because I did work. I lifted it there, gave it that energy, and then I let it go, and it converted that energy into other forms. Okay? He did a similar experiment, a little bit more complex, with these masses, and he had a jar that was just full of air with these blades that would rotate as the masses fell. So again, the masses had potential energy. As they fell, they turned it into kinetic energy, which turned the blades, which moved through the air, creating friction, okay? And then it changed the temperature inside the jar. Okay. All right. I would like you guys right now to please answer the questions that are here. So 2, 3, 4, 6, 9, 12, and 13, and 14. Okay, they're mostly stuff you can just look up in those notes. Okay, so I'll just write them up here because you can't see them all. 2, 3, 4, 6. Okay, and I'll give you the rest of class to work on those. Okay, and we'll talk about them probably tomorrow.